So let me start with the second part of the tutorial. So I'll be talking about this topic of generative adversarial networks, which I think is another topic in machine learning that combines game theory and deep learning. The goal of this part of the talk is to basically just present the whole framework of generative adversarial networks to people that are not familiar with this topic. So if you're very familiar, maybe most of the talk will not be very interesting to you. But given that the audience is targeted to the EC audience, I thought of giving like an introductory overview to the topic. And then I'll also mention two main problems that people face when trying to train these generative adversarial networks that are related to topics that maybe people in the EC community have studied. And I will also give some partial solutions that have emerged and some partial lines of work that have emerged over the past 2 years, some of them which were actually contributed by people from the EC community. All right. I won't have time to go into the technical details of each of these contributions, but I'll give some brief intuitions and mostly talk about what are general open directions in these problems. And if you're interested in references, I'll be happy to send you a follow-up email. Please send me an email. So what are generative adversarial networks? So the general problem that we're trying to address is learning distributions. So the standard, maybe problem that people in the theory community might have, faced is suppose that you have data and you're trying to understand what is the distribution that this data came from. And maybe people are familiar with learning, mixtures of Gaussians, maybe in 1D or in 2D or whatever, in high dimensions. And there you're going to have, these points, and you want to try to find some sort of like parametric likelihood function and fit the parameters of this likelihood function so that they match the density of the empirical density of the data that you saw. So this is fine when you have like 1, 2, 3 dimensions, even maybe 100 dimensions. But what happens if your goal is to try to fit distributions of complex structured data sets, such as images? So what if I tell you here is a set of images? Can you give me a model, a generative model, a probability distribution from which these images were generated? So can you find what is the underlying generative model that generates distributions of faces of people? Now, this is a very complex, data landscape. Even if you view it, for example, on the pixels page, you have like maybe 100 by 100 pixels. These are all of your, or each one of these pixels is your dimension. There may be like three layers, RGB, the color, and each of those layers there is a number, and you're trying to find this 100 by 100 by 3 dimensional distribution, which typically lives in a much, much, much lower dimensional, manifold of this high dimensional space. So typically, and the goal is, given this sort of like data set, can you sample new images from that same distribution? So can you generate new faces that look like, new images that look like faces of people? But, don't just memorize the input images, but really sample from the distribution of faces of people in the world. Maybe you can sample a new face that does not exist in your data set. If you actually did a good job of capturing what was this underlying distribution, this latent distribution that you do not see, most probably you'll be able to generate new faces. Okay. What would be applications of, if you were able to accomplish this task, which seems kind of magical to me, what could be good applications of this result? So, one straightforward application is that you'll be able to generate, to augment your training data sets and have bigger data sets. And so you'll be able maybe to avoid overfitting when you're training your models, and maybe, train on larger data sets where you use also these realistic types of images. Other places where this has actually been starting to be used is that you could use these structured, samples, these fake samples, as sort of like a rapid prototyping approach. Maybe you have like experts that try to manufacture some 3D object, maybe some part of a machine, and now you want to say, I want to optimize over the space of all possible structures. And what you can do is you can say, give me 100 possible structures designed by an expert, and I'm going to feed generative distributions of those designs, and then I'm going to sample a new design. And then you can go and test the properties of that design in practice. And so you can do some sort of like rapid prototyping and searching over the set of feasible solutions of an actual object, right, that you want to manufacture. So that's another place where this actually has been starting to be used. Another place where you can apply this is when you want to fill in missing data. So if I had a way of generating pictures, especially if I had a way of generating pictures conditional on contexts, so then I can use that in film editing. I can say, try to fit a distribution of what is the next frame of a film given the last few sets of frames of a film. And then I can generate new frames when I don't have them. And then I could maybe fill in missing frames and produce a high resolution video from a low resolution one. Similarly, in image editing, I might have a low resolution image, but if you manage to fit a distribution for the missing pixels, you could maybe generate these missing pixels through this learned distribution and create a high resolution image. So there are several potential applications of learning such generative models of complex structured data. And that's why a lot of people in machine learning are interested in addressing exactly this problem. Okay. So how would you start attacking this problem? It's a bit unreasonable to say that I'm going to build a parametric likelihood model of this 100 by 100 by 3-dimensional distribution. I most probably do not want to go to this parametric approach and try to optimize the parameters. The first observation is that you don't really want to learn an actual likelihood of the distribution. What you really want is just to be able to sample from the distribution. So you don't really need to learn a closed form solution for the likelihood. All you need is some black box, and this is the topic of implicit density learning. All you need is some black box that takes as input random noise, so takes an image that is just Gaussian white noise, passes it through some black box, which could be some complicated function, and at the output, you get an image. And the goal is that when this black box takes as input this random noise and it takes a random draw of this noise, the output will be a random draw of the underlying distribution of images from which your training data were generated from, right? So maybe here you can take this input and generate images of a dog. Right? So that's the implicit density learning framework. And what your task is now is to find what is this function g that takes as input random noise, massages it, and comes up with an actual image that looks like a realistic image of a dog. So the main question now is, how do we optimize this implicit density model? Observe here that if I learn a g, it's not that I have an actual parametric likelihood function. I don't know what the likelihood is. If you tell me what is the likelihood of this image, I might need to integrate over regions, look at random. Maybe I can do some sort of Monte Carlo approximation where I draw random noises. I see whether there was some images in some nearby distances, but that's definitely not a likelihood model. It's an implicit density model, but it's good enough if your whole goal is to sample new images. So again, how do we optimize this g? If this g, all that it does is that it samples from it claims to be sampling from the underlying distribution. So unlike explicit likelihood approaches, we can't run standard techniques such as maximum likelihood. We cannot just formulate a log likelihood, a log likelihood loss and maximize the likelihood of the training data that we saw, based on this parametric form that we have. We somehow need to formulate an objective that tries to capture the distance between two distributions. One is the distribution of the real data, and the other is the distribution that is the result of passing random noise through this g and coming up with the output of that g function. So if we could, if we formulate some notion of distance between two distributions that are given to us in this implicit form, then we can try to find a g that minimizes this distance function between the implicit sampling distribution and the true distribution of our data. And this is here is like the main idea behind the generative adversarial networks. If the sampling distribution based on g was actually very close to the true distribution that your real data were generated from, then if I am an adversary, I wouldn't be able to distinguish if an image that came out of this generator and that came out of the real training data set, whether it came from the generator or from the real training data set, right? So as an adversary, I wouldn't have this distinguishing ability. And so this is how learning a distribution now becomes a game, between a generator that tries to generate samples based on input random noise and some discriminator who tries to distinguish whether the sample came from the true training data set or from this generator. So that's the main idea behind generative adversarial networks. You create a discriminator that tries to classify images between true and fake. And then the generator tries to find a distribution such that the discriminator cannot distinguish between that and the true distribution. So, or equivalently, such that the discriminator, when trying to do this classification task, has a very large classification loss. Right. So this is the main idea. And here now, let me just do some basic math. So how do we formulate this explicitly? So this is the zero-sum game formulation of generative adversarial networks as was originally defined by this paper of Ian Goodfellow. So you have this discriminator who's trying to maximize a classification, maximize a classification reward, minimize a classification loss. And one of the standard classification losses that you can think of for binary classification is what is known as the logistic loss. What is the logistic loss? It says, for all of the images that came from the true distribution, the label for that image is 1 because it's a true image. And for that, the discriminator, who is this function d of x, tries to output a number between 0 and 1. And his goal is to output a number as close to 1 as possible whenever x is a real image, and a number as close to 0 as possible whenever the x is coming from the fake. And this is captured exactly by this function over here. Of course, there's a penalty, which is this log function, but that's not so important. The most important part of that is that this function is some sort of increasing concave function that says, if an image came from the real distribution, try to output a number as close to 1 as possible. If an image came from the fake distribution, try to output a number as close to 0 as possible. Okay. So this is the logistic loss that the discriminator is trying to, actually it's a logistic reward, that the discriminator is trying to maximize. Okay. So the discriminator wants to maximize this over all possible such functions that take as input the x and output a number, right? Of course, the discriminator does not know the label. It only knows, either just the image, which is x, or the output of g when the input of g is some random noise. Okay. So the discriminator wants to maximize this over possible functions d, and the generator wants to minimize this over all possible functions g. G's are these generating functions. And in some sense, and more importantly, the generator actually wants to, guard against any possible discriminator that could distinguish the data. So it's not really that the generator wants to minimize this VD of G for some fixed D. The generator wants to minimize this over all possible discriminators that, could come and try to distinguish his distribution from the true distribution. So you have this min-max problem again, where you're trying to minimize over functions G, generating functions G of the maximum possible, discrimination that the discriminator can do for that distribution G. Okay. Any questions so far? Okay. Good. Now, another interesting, so this is this is the original formulation of GANs. One interesting theoretical aspect of this formulation is that even though we phrased it as this zero-sum game between a generator and a discriminator, which would be very helpful when we actually try to solve the task over, over spaces of images, at this point we're just like looking at learning distributions in some abstract space, and at this level of generality, you can actually connect this framework to a framework of learning a distribution G that minimizes some distance metric between distributions and minimizes and finds a G that is the closest distribution with respect to that distance metric to the true distribution. And what is this implicit distance metric? You can show that you can actually characterize the maximum if D is arbitrarily powerful. So if the discriminator could be any possible function out there, then you can explicitly characterize what is the optimal best response of D given a distribution G. That best response basically says, for every x, I'm going to predict the density ratio of the density that the true data are putting over there over the density of the true data plus the fake data. So it's the proportion of like true data that of the proportion of true density for that x, which is could be an arbitrarily complex function, but that's the actual best response. And if you replace d with this best response, then this maximum over d function takes the form of what is known as the Jensen-Shannon divergence between two distributions, which is sort of like a symmetrized KL divergence, measures the KL divergence of the real distribution with respect to this mixture of real and fake, plus the KL divergence of the fake distribution with this mixture of real and fake. So this is this is the notion of distance that is implied by this framework between two distributions. And what GANs are actually trying to do in the idealized world is try to find a distribution that minimizes this notion of distance, find a distribution that is the closest to the truth with respect to this notion of distance. Okay. So this was the case for this discriminator generator, but as I said, it's not specific to that. And in fact, like, subsequent papers generalized this framework and said, why put the log function over there? We can put an arbitrary, monotone concave function phi. In fact, a very particular appealing function that people have used is this, boils down to this notion of a Wasserstein GAN, where basically you're just using the identity phi as opposed to the log. One reason why people didn't like the log is because the log sort of like blows up when the discriminator predicts close to 0, right? It goes to infinity, and so the gradient of the generator blows up. And trying to train a neural network where the gradient can actually blow up is very problematic and typically led to overshooting when you take a gradient step and a lot of instabilities in neural net training. So that's why they didn't like the log. Even the very first paper formulated this discriminator generator formulation, but then said, we're not going to do that. We're actually going to solve a non-zero sum game where they changed what the loss of the generator is so that you don't get this blow up. So even though they analyzed this zero-sum game, they switched quickly to a non-zero sum formulation to avoid this gradient blowing up. But this actual formulation has the nice property that it's, even this zero-sum theoretical formulation that they could sort of analyze did not have this problem when it was translated to training a neural network. And the other nice thing is that if you actually put here the identity function as this phi function, this loss function simplifies to just trying to this following reward, which basically says, what does the discriminator trying to do? They're trying to find some function whose expected value under the true distribution is far away from its expected value under the fake distribution, right? So that's exactly what this loss function is saying. The discriminator is trying to find a function such that if I integrate that function with respect to the true data, that number is going to be very different from the number that I get if I integrate that function under the fake data. Right? This type of function typically is called the moment of the distribution. Like you could have like the first moment, the second moment, you could have any arbitrary moment, right? And basically what this Wasserstein GAN is saying is like the discriminator is trying to find a moment that is different under the fake and under the true distribution. Okay. And as long as I'm, if the discriminator is powerful enough to test many of those moments, most probably if you manage to prove that, all of these moments are small between two distributions, then most probably their actual, these distributions are actually, intuitively near each other, right? So in some strong sense. In fact, there is this nice also theorem, this characterization of these Wasserstein GANs that says that if the discriminator corresponds to all possible one-Lipschitz functions, then minimizing this quantity over all such one-Lipschitz functions is equivalent to the earth mover distance, which maybe many people are familiar with, which basically says I have two distributions, try to couple these distributions so that the marginals are preserved, and such that if I draw 2 points from this joint distribution, the L1 distance between these 2 points is minimized. Equivalently, this is trying to say here is a density that I have, here's a target density. Try to massage this density over here to look like this one, while minimizing the, the cost of transportation of density, which is measured by the L1 norm. And if the best possible such coupling is the earth mover distance between the two distributions. And if the discriminator was able to choose all possible functions among one Lipschitz functions, then minimizing over G the maximum overall D of this thing is equivalent to finding a distance which is close to the true distribution under the earth mover distance. So finding a distribution which is close to the true distribution under the earth mover distance. Of course, in practice, we're never going to have a discriminator that is as powerful as all possible one Lipschitz functions for many reasons. First, it's hard to optimize over all possible such functions. Second, we don't really have infinite amount of data, which here, implicitly I'm assuming that I have infinite amount of real data and infinite amount of fake data. And so when you go to finite samples, you have generalization error problems. If your discriminator is very powerful, then minimizing the empirical version of that distance can be very different from minimizing the population, because the discriminator is sort of like so powerful that it can overfit to the training data. So what people are doing, what the real GAN framework is instead of like trying to solve this minimax game over all possible functions D and G, let's try to solve this minimax game over functions that look like neural networks. So we're going to parameterize both of these functions, the discriminator and the generator, by a neural network that is flexible enough. It's deep, it's wide, whatever. And these are the the parameters. W is the parameter of the neural net of the discriminator, and theta is the parameter of the neural net of the generator. And in fact, like there's been also some interesting theoretical work by Aurora et al. 2 years ago that was also trying to argue generalization error bounds for these types of neural nets as a function of the number of parameters in the neural network. Basically trying to show that even though minimizing the earth mover distance can be susceptible to overfitting to training data, if you minimize over neural nets with a bounded number of parameters, you can get some decent generalization. Of course, it's a theoretical result, and the guarantees that you get might not translate to reasonable numbers in practice, but there is some formal reasoning of why you might want to restrict yourselves both for the generator and the discriminator to some parametric class. Now, once you do that, one question that you might ask is, okay, so I restricted the discriminator to not be this super powerful discriminator, but to be represented by a neural net. One question that might arise then is like, okay, if I tell you that these two distributions are close to each other with such a not so powerful discriminator, does that really mean that you recovered the true distribution? Is this distance strong enough to really mean distance in distribution? Typically the answer will be yes, as long as the discriminator can test many moments of the underlying data, then it will be strong enough to identify the parameters of the underlying distribution. Of course, this is a very hand-waving argument, but that's the whole idea behind GANs, that if we put a very flexible discriminator, we'll be able to test all possible moments of an image, and if some moment of an image does not match under the true and the fake data, the discriminator will be able to identify that. Just as a very simple example, let me give you some, two very stylized examples of how you can learn a distribution in this framework, and how you actually need if in simple examples you actually need discriminators that are also very simple. And so you would expect that if the distribution you're trying to learn is not like an arbitrary distribution, testing a small set of moments can actually give the correct result. Of course, these examples I'm going to give are very stylized, but just to get a handle of what is the actual game that is being played here, such that in the end the outcome is a model G that really learned the true distribution. So let's look at this very simple example of trying to learn the mean of a multidimensional distribution. We know that the true data are drawn from some normal with some mean V and some identity covariance matrix. And our goal is to learn this parameter V, which is the mean. Now, in this situation, actually, it suffices that the discriminator is the space of all possible linear functions. You don't need anything complicated. You just need to be able to test, first moments. And suppose that the generator, so here, the discriminator is parameterized by this W, and it tests, functions that look like an inner product between W and the data point. Okay. And the generator, let's say, it's a generator that takes as input random noise, and since we're trying to just learn a mean, takes as input data, a random noise which is normal centered at 0, and tries to displace it so that the displacement exactly matches the mean of the underlying distribution. Right? So the generator is also a very simple function that takes as input z and spits out z plus theta. Okay. So what is the Wasserstein-GAN? The Wasserstein-GAN objective in this very simple formulation? You can write down these equations. You can take these expectations now. They're very simple. You end up with this objective function, where W is the strategy of the discriminator, and theta is the strategy of the generator. And they're playing this game, this inner product game, where the W player wants to maximize this, and the theta player wants to minimize this. It's obvious to see that the only solution, the only equilibrium of this game is for the generator to choose theta equals v, because for any other solution, the discriminator could pick, the sign of v minus theta and give get a humongous reward, or the generator is going to get a large loss. So the unique solution of this game is for the discriminator to choose the true mean as the output, and so under this sense, the generator actually learned the correct distribution. Okay, very stylized example, but it's sort of to say that in simple cases, this whole approach of a Wasserstein-GANs will not fail. And you can do the same exercise when you're not trying to learn a mean. Say you want to learn a covariance matrix. Now, of course, because you're trying to learn a correlation between coordinates of your distribution, you also need to test second moments. So say now the discriminator is a quadratic function as opposed to a linear function, and the generator now takes as input random noise and tries to translate it with some matrix V so that the output is the true data distribution. Right? So now the generator is trying to learn a correlation matrix, a covariance matrix, and if you write down the Wasserstein-GAN, you get exactly the same looking type of zero-sum game, where if the generator did not choose his translation V such that if you take this inner product, it matches exactly the covariance structure of the true data, then the discriminator can penalize the generator, and so on at the unique equilibrium of this zero-sum game, it has to be that the generator learned a translation whose covariance, such that the implied covariance matrix matches the true data. Right? Okay, so these are just two simple examples to show that you can learn distributions. Of course, this is assuming that you found an equilibrium of this zero-sum game. And even in this simple situation, it's not, like even this situation, the generator's problem is trying to find an eigenvalue, a decomposition of the covariance matrix into V and V transpose. So it's not like a very simple task for the generator. It's essentially implicitly performing this linear algebra operation of finding the decomposition of a covariance matrix. And if you go to more complicated discriminator-generator pairs, the biggest question is how do you optimize this minimax problem? How do you find a solution to this minimax problem? Okay, so that's the next part in this talk. So how are we going to optimize this minimax problem when the generator and the discriminator are represented by a neural network? Any questions so far? So the first point is that we don't have infinite amount of data. We have finite, we have a finite sample of data. So the first step in making this taking this idealized approach to practice is to replace these expectations that I was describing so far with empirical averages. So that's the standard approach. You take, instead of taking here an expectation over the real distribution, you replace it with an empirical average over real data points that you have. And here, instead of taking an expectation over the random noise, you sample n random noise inputs, and you take an empirical average of the output of the generator under these n random noise inputs. Okay. So now we can sort of we phrased our problem in terms of given a data set, what is the minimax, the proxy version of the hypothetical objective function we want to minimize. Whether these two are close to each other is more of a generalization question, a generalization error question. So I won't touch upon that so much. There's this work of Aurora et al., for example, that gives some results. This is more like more a traditional statistical learning theory question. So I won't go so much into such generalization errors. But even in this empirical formulation, it's not clear how you're going to optimize this minimax game when both D and G are a neural net. And this also goes to the types of problems that arise in the first part. You have one player trying to optimize a neural net. Over in the first part, the other player was playing a distribution over losses. Here, the other player is not playing a distribution over losses. It's actually playing, it's actually choosing a moment to test between the true and the fake distribution. And this moment is parameterized by another neural net. So both players are optimizing over neural nets. And the only way that practitioners know how to train neural nets is through first-order methods, is through gradient descent approaches. So apply some gradient descent dynamics to train a neural net based on, and typically stochastic gradient descent, where at every iteration, instead of calculating the gradient on all of the data points, I'm going to get a mini batch of the data, a subsample of the data, and calculate the empirical gradient of that subsample and take a gradient step. But now we have this problem that this loss is not a standard loss that people in neural networks are facing, for example, in a regression problem, because the inner optimization is also a neural net maximization problem. And it's a bit hard given that you need to train the outer layer, the learner, the distribution neural net, you need to train it for like 1,000 iterations. If for every one of those 1,000 iterations, you would need to train another 1,000 iterations your discriminator, it's unrealistic to take such an approach of fully solving the inner optimization and then solving the outer optimization, having solved the inner optimization. Of a what? There's no notion of regularization. Here, implicitly, the regularization is through the small number of parameters of a neural net, which is not true. But yes, you could add other regularization parameters to your neural net, such as the standard, L2, L1 penalties on the weights of a neural net. You could do things like that to avoid overfitting. You would add it to just the stochastic gradient problems that that you're using. And I'll briefly talk about some other types of penalty functions that people have used in practice, but most of them are not the standard. You can also add the standard, regularization parameters, which are essentially shrinking the hypothesis space that G and D live in. Right? Okay, so now the inner optimization is also this weird neural net, so I cannot fully solve the inner thing and then solve the outer thing through a first-order method. So what do? The basic idea that's coming from this first paper on generative adversarial networks is, take the perspective that you don't really want to solve the minimax game. All you really want to solve is you rather just solve an equilibrium of the zero-sum game that is implied by this minimax problem. So treat this as a real game between the discriminator and the generator, which is not what you really care about. You don't really care about finding an equilibrium. All you care is finding a solution to the minimax problem. But the reason why you go to this game formulation is so that you can simplify sort of like the optimization problem. And why is that? Because once you take this perspective of a zero-sum game between a discriminator and a generator, you can take this idea from finding an equilibrium of a zero-sum game through simultaneous no-regret dynamics and apply that in a hand-waving manner to this complicated zero-sum game defined by the generator and the discriminator. So we know that if you have a very simple, say, bilinear game, or any convex-concave game, and you apply no-regret dynamics for the one player, no-regret dynamics for the other player, the averages are going to converge to an equilibrium. So in some sense, doing no-regret dynamics on both players can actually find an equilibrium of the zero-sum game. And so let's take that intuition and translate it into this very complicated, not convex-concave zero-sum game defined by the discriminator and the generator. That's the basic idea behind this first paper. And then you can simply apply this gradient-based dynamics for both of these players simultaneously, and see where you ended up and see what happens. So that's the basic idea. So you formulate this either discriminator GANs with a logistic loss, or these Wasserstein GANs with this moment-based loss. You treat it as a zero-sum game between a discriminator and the generator, and you apply simultaneous no-regret dynamics or gradient-based dynamics, and you look at your final generator and you see, is this generator sampling good images for me? So that's the basic idea. So we now have all of the ingredients. So the question is, does this work? Like, does it following all of these things? Can we actually train generator neural nets that actually give realistic-looking images? And after several years of improvements and tweaks and hyperparameter tunings of how you tweak these simultaneous dynamics, because it's much harder than tweaking the hyperparameters of a regression loss. Even when you try to train a neural net for solving a regression or a classification problem, there's so many hyperparameters you need to optimize over, like what's your gradient step size, like how deep or how wide. Now you even have this extra complication of this adversary and the simultaneous gradient updates that, like your loss function is not stable anymore. It's changing from time to time. So there are even more tweaks you need to do. But, the state of the art has actually improved a lot. And by now we can actually get very realistic images of people's faces, right? So you can make this approach sort of work after you tweak it a lot. Okay? And similarly, you can generate, there's like also a lot of improvement over time. You can generate realistic looking images of dogs. Okay? And this actual approach has been so popular that like almost every month there are like 30 papers these are 30 papers that have a GAN that has a different name, right? So this is like the A GAN, the B GAN, this is how many, currently there are 510 papers that have a named GAN, and each of them trying to solve a different, sub-problem through this general approach. And, there's been some applications. Most of them are more like expository. So for instance, there's been some applications on actually finding high resolution images from low resolution ones. So you can see here, this is the original high resolution, and this is the, the high resolution that was derived by some state-of-the-art GAN. You can do things like a person draws a sketch, and then the generator sort of like samples an image based on that, conditional on that sketch, and samples an image of a mountain. You can do other applications where you draw on a face some sketch, and the generator draws a sample of some editing that you might have wanted to do on that part of the face, and edits the face automatically, or predicts the next frame in a film, or finds a real, you sketch a product and it finds what an actual product that exists out there, and so on and so forth. I don't know what to say. I don't know what you're talking about. Who uses Snapchat? Anyway, why are you using Snapchat? Okay. So these are some applications that you can apply GANs to. But as I said, there's so many things that you need to tweak to be able to succeed in each of these applications, and each of those applications might need different tweaks and different hyperparameters and different architectures, and that's one of the reasons why there's so many GAN papers, because for each of those applications people found that this type of sub-approach worked better and this other didn't work, and so on and so forth. But so deep down there are some main hurdles in GAN training that actually relate to problems that maybe the EC community is capable of providing some new viewpoint, and so that's what I want to talk about next. What are the main hurdles in GAN training? Okay, so what are the two main problems that maybe people in this audience might have ideas of how to tackle? So the first problem is this relates to unstable game dynamics. So look at the very simple example that we had in the introduction of learning the mean of a distribution, and even ignore the sampling error that comes from data. Suppose that we're in the population limit, and suppose that we apply vanilla gradient descent dynamics to this, we update the generator using gradient descent, and we update the discriminator using gradient descent for this simple bilinear game that was W times V minus theta. And these are the dynamics that you get, right? So this is the parameters of the discriminator, and these are the parameters of the generator. Say here you have a two-dimensional distribution, and you're trying to learn these two means. So what you see here is that at no point in time was the generator ever, did the generator ever find the true means? these dynamics were constantly oscillating around the, potentially around the true means of the distribution, but we never really found those true means, right? No matter where we stop these dynamics, we're never gonna spit out the true means of the underlying distribution. And this is no surprise because, as theoreticians, we know from no-regret learning in zero-sum games that the theorems really only guarantee that if you try to solve zero-sum games with no-regret learning, it's only the average of these strategies that converge to an equilibrium. It's, it's not the last iterate. It's none of these, it could be the case that at no point the generator had really the true distribution, but if you average over these parameters of the generator, you actually get back the correct distribution. So that's one problem. How do we reconcile these, theoretical guarantees that only talk about averages of strategies with simultaneous gradient descent in neural nets where averaging over the parameters of a neural net actually is nonsense. You'll get back nothing. So how do we reconcile this discrepancy between how can I average a neural net, or what else can I do instead of using algorithms that only give guarantees for averages? So that's one main hurdle that a lot of people in GANs actually recognize. And if you look at tutorials given about GANs by the actual people that are applying this in practice, this is one problem that they recognize. And another problem is that the fact that the minimax problem that you're faced is not convex concave, and so going from the minimax to an equilibrium solution is actually without loss of is not without loss of generality. It's not without loss of quality, right? So in the sense that because the problem is not convex concave, it's no longer true that we can apply von Neumann's min-max theorem and say that max min is equal to min max. There might be a duality gap between the max min and the min max, which will avoid ever finding a pure equilibrium in the discriminator and the generator. So it's not clear that there always exists an equilibrium in this game between a generator and discriminator in pure strategies, where by pure strategies I mean that there exists a single weight for the parameters of the discriminator and a single weight for the parameters of the generator, such that the two are in equilibrium. Right? Maybe you need to look at mixed strategies over neural nets, and how would you do that? How would you randomize over neural nets? So that's the problem of maybe potential inexistence of pure equilibria. And another problem that is more tailored to how you optimize, how you find this equilibria, is that you might have this spurious local equilibria. For instance, in some regime of the discriminator, maybe the gradient of the generator vanishes completely and you have an approximate critical point for the generator. And so because you're only solving finding equilibria through local dynamics, you're only guaranteed to find local equilibria. By local I mean that no epsilon best response around a point, around your current point, is improving. So a local equilibrium does not imply a global equilibrium, and this might create spurious local equilibria that do not correspond to solutions to the minimax problem. And this is actually a real problem again that people are facing. For instance, when you suppose that you started with a generator that is not very flexible enough, say the generator can only output a Gaussian around some set of points. Maybe if you solve the min-max, you'll find the Gaussian that is closest in distance to the true distribution. But if you actually exchange the min-max with the max-min, this completely changes the solutions that you're going to find. In the sense that now, if the discriminator gets to play first, the discriminator will have some probability of saying it's a true or a fake at every part of your space. And then what the generator is going to try to do is going to try to take this Gaussian and place it all on the parts of the space that the discriminator says it's most probably true. Right? So now you're going to have this generator who's trying to follow the discriminator, always placing almost all of its mass on the parts of the space where the discriminator is saying it's most probably real. And you have this chase of the generator chasing around the discriminator, and what you get back is again such sort of limit cycle points where, say, your true distribution was this mixture of Gaussians in this two-dimensional space. What ends up happening is that the generator ends up cycling, spitting out a Gaussian centered at some point, as opposed to finding this mixture of Gaussians. Right? So going from max-min to min-max might be problematic. It might lead to extra cycling, and it basically leads to another problem that has this keyword mode collapse in GAN training. Mode collapse basically is sort of equivalent to saying you have some mixture distribution and you only output a part of the mixture, not everything, right? So maybe you get as input like distributions of digits, and then you only output nines or ones, and you don't output the whole mixture. So these types of non-existence of equilibria can lead to such mode collapse. And as I said, there was this other problem of spurious local equilibria due to this vanishing of the gradients, and so that was another problem that people were facing. So good. So now let me try to go into some approaches that people have taken in the past for addressing some of these problems, both theoretical and practical, like both tricks that people have applied in practice and some of the theoretical work that has been done. But I should say ahead of time that in no way any of these problems is fully solved. We just have solutions for stylized versions of the problem with several assumptions and indications of that this intuition that comes from the stylized version actually leads to an experimental improvement. So this is the type of, this is sort of like how most of the GAN papers are actually going. You have some theoretical analysis in a stylized version of the world, and you actually do some experiments translating some of the key findings, and you say, I get a better solution. That is a bit problematic because even judging the quality of the solution is hard in GANs. How would you judge that the distribution that you found is actually a good one? The people have devised these types of scores so that you can get improvements on these scores, but nothing is very satisfying. So maybe pushing the state of the art in theory might be a good opportunity here. So unstable dynamics, again, so this I think is an opportunity for the EC community that tries to analyze, gradient-based solutions or like continuous optimization solutions for games and for games with continuous action spaces. Maybe there are ideas from this theoretical research area that can be translated to new versions of GAN algorithms. And already I'm going to talk about some ideas that have been applied and some improvements that people have gotten. So one line of work in this trying to address this problem is essentially trying to solve the following theoretical problem. Can we find algorithms that have last iterate convergence in zero-sum games? Can we find gradient first order sort of dynamics in zero-sum games so that if both players employ this type of first order algorithm, then not only the averages of the strategies converge to an equilibrium, but the last solution converges to an equilibrium. Okay? So that's one theoretical question that you can ask. And then you can say, okay, here is an algorithm that actually has this last iterate convergence. Let's translate what would be the analog of that algorithm for training a neural net and see how it performs in practice. And the reason why last iterate is important is because there is no clear way of averaging the parameters of a neural net. But if you go ahead. Yeah, so that would be one way of finding a mixture of, or like maybe you can say I'm going to randomly sum, so that I'm going to define the mixture of a window of neural nets so that I can get back mixtures. That has been actually, one paper has tried to analyze something like that. One problem with that is that you need to keep track of a huge amount of neural nets, right? And if each neural net has a large memory, it requires a lot of memory to even store the weights. That's not very practical. Yeah, but this is one direction. Maybe you can say I'm going to implicitly define some mixture of a small number of neural nets. And these are ideas that I'm also going to go into. Some people have tried, right? But yes. But if I could give you an algorithm that actually has last iterate convergence, and I could guarantee that the final one, you get a big boost in at least memory usage, right? So, or if I guarantee you that the last 10 solutions are good, you know that like you only need to store the last 10 solutions. If your dynamics look like the oscillations before and you don't know where to stop, it's more problematic. So we actually tried to tackle this problem with Kostas and two students from MIT a year or so back. We tried to employ some ideas from no regret learning in games and tried to use this algorithm that actually had fast convergence in games, which was called optimistic mirror descent, where basically the only change that you do to gradient descent is that you sort of upweight the gradient in the last iteration, and this translates to saying I'm going to take twice a gradient step based on the last gradient, and then I'm going to subtract the gradient from the iteration one thing before, so that I only put more weight on the final gradient information. So that's one simple modification to gradient descent. It's equivalent to sort of taking like 2 steps of gradient descent with using the last gradient, and this is more of a way of writing it as a recursive solution. So this was an algorithm that we had proven, like that Rachlin and Sridharan back in 2013 had shown that converges faster in games, so it gets 1/t rates. And we all, like in a paper that we had also at NIPS, we saw that this faster convergence rate extends to non-zero-sum games. But what was important that we also observed that these types of dynamics actually do not cycle in zero-sum games. And so when we saw this problem of like cycling in GANs, we thought that maybe we can prove that, formally prove that these types of gradient-based dynamics do not have limit cycles and actually converge in terms of the last iterate. And this was the first theoretical result that we proved there. We actually saw that for bilinear games, even though gradient descent dynamics can cycle, as you saw in the previous example, these optimistic gradient descent dynamics converge in terms of the last iterate. And similar results were shown in much more general setups in follow-up work. So for example, follow-up work of Kostis also showed that this extends beyond bilinear to any linear programming problem or to strongly convex concave. Youngest Stokes analyzed to strongly convex concave settings and so on and so forth. Okay. Yeah. Why it works? Yeah. So the intuition here is that you're sort of like when you're taking when you do a gradient step twice on the last iteration, it's sort of as if you're saying I'm gonna predict what the gradient will be in the next period and take a gradient step from there. So I'm going to use the last gradient as a proxy for the next gradient. And so I'm sort of like trying to look ahead, what would be my gradient in the next period? And this actually helps because you're in a game, and if you can predict that in the next period you guys are going to be in this situation, you will try to correct it. And because you're going to do it beforehand, instead of like instead of cycling all the time, you're going to dampen these cycles, and you're going to spiral in towards an equilibrium. So that's and this is actually the intuition behind another algorithm that we didn't know when we wrote this paper, but which actually dates back to very early work in solving variational inequalities by Korpelevich, which was basically saying do something similar, not exactly that, but basically take a gradient step, look where you ended for both players, look where you ended up, take another gradient step from there, and apply that gradient to your original solution. So there are some subtle differences between these two. The first one double counts the last gradient. The other one tries to find a prediction of the next gradient by taking a gradient step from the current solution. So the two are slightly different but have the same intuition of trying to predict where we're going to end up in the next period and correct from there. And so these were some of the algorithms. We actually, both of these papers, all of these papers take these algorithms and translate them into how they would look when you take this optimism, for example. How would you adapt the standard algorithms that people are using for training GANs to add such an optimism behavior? And we propose, for example, here a variant of this algorithm that's very popular in neural net training called Adam to augment it with an optimistic step. Similarly, people in these papers adapted Adam to augment it with an extra gradient step, and you would see improvements in performance with respect to the scores that people are using out there when you make these modifications. So these are some theoretical results that also have some improvement in practice, and of course you don't really there's some improvement. It's not that they really solve the problem. Go ahead. Both of them. I just saw the updates of one player, but both of them are doing the same thing. Yes. You take so in the top one, I believe that the gradient in the next period is going to be the same as the previous period. Why do I believe that? Because people are doing gradient descent, and so they don't really change their parameters a lot. So whether I take a gradient here or a gradient there, it's pretty much the same. So that's a stability of gradient descent. And I use that to predict what my next gradient will be. as a function of this gradient. I basically say it's going to be the same. So that's the first idea. The other idea actually does do a gradient step for both players. And so you actually do need to transmit information to say, I'm going to do a gradient step for both neural nets. Here is the gradient, some centralized, authority does gradient step for both players and then says, here's the gradient from that gradient step to the generating discriminator. And then they take a gradient step from their original point in that direction. Right? So it's less maybe decentralized if that's what you're hinting. And then some even more recent work that I just recently came across, like it was uploaded a few weeks back, maybe. So Jacob Abernethy, who was also working in this area, also managed to prove some fast last iterate rates with a different algorithm that actually also has a very different flavor. Instead of now trying to to solve this equilibrium through simultaneous dynamics, you're going to try to find a critical point of the local equilibrium conditions. You're going to try to find a point where the gradients of both players vanish, right? So, this is a sufficient condition for a local equilibrium. And instead of trying to minimize simultaneously both players, just try to minimize the L2 norm of the gradient of both players. And how you're going to optimize the L2 norm of the gradient of both players? Do gradient descent on this loss. And then you're going to get some sort of second order method where the gradient update sort of depends on the Hessian of the losses. And so that's another approach, and they managed to show some even fast rates for sort of linear rates, the distance to an equilibrium decays exponentially. Similar rates, I guess, so follow-up work also of Kostisa, I think, also showed that you can get such exponential sort of rates using controlled dynamical system theory arguments. Anyway. Yeah, so, and that also gives me a segue to another type of line of work that people are analyzing here. Instead of finding explicit rates of the last iterate convergence, maybe we can view these dynamics through some sort of dynamical system approximations, idealize dynamics, and try to understand what are the limit points of these gradient dynamics. And through using techniques from dynamical system theory, maybe we can show that the only local stable points of these dynamics are good solutions to the original minimax problem. And so this was also, an approach that was taken by some early work by people in the machine learning community, and also Mertikopoulos et al. Has also done, and I believe Georgios Piliouros, who's also from the EC community, has done a lot of work on this, analyzing the stable points of some such optimistic dynamics. Here, they also actually managed to analyze this optimistic gradient descent through this dynamical system formulation. And another more ad hoc, I guess I would say, but more from a practitioner's point of view, some of the early work on trying to address this cycling problem actually tried to regularize the loss function, which is not a bad idea, but and it actually, there are some nice intuition, but less theoretical results in this line of work. So for example, one of the first papers that tried to address this cycling in Wasserstein GANs was saying this cycling most probably comes from the fact that the discriminator is very powerful, and that's why we cycle. So let's try to make the discriminator less powerful. Let's use the intuition from the connection between Wasserstein GANs and the earth mover distance. There we know that we need to be testing one Lipschitz functions. One Lipschitz functions actually have a small gradient. The gradient of the function with respect to its input must be small. So let's add the penalty to the loss function that is the expected gradient of the actual discriminator with respect to its input. Not with respect to its parameters, but with respect to its input. So they add such a gradient penalty, which sort of enforces, it's a smooth enforcing constraint, so that the discriminator is a smooth function and not a very discontinuous function. And so that sort of stabilized a bit the dynamics. In our we actually tried things like that in the paper we did on this very simple example of learning the mean of a distribution that actually doesn't really improve on the limit cycling for this particular example, but maybe for more realistic looking GAN settings, this can lead to an improvement. But it doesn't definitely solve the problem in the worst case, because we have this example that shows that this gradient penalty is not a universal solution. Another approach that I also recently came across is trying to be even more formal on how you're going to add this regularization to your loss function. Basically, again, uses this connection with the earth mover distance and this optimal transport theory that's equivalent to the Wasserstein GAN. And now saying instead of trying to find couplings between two distributions such that the L1 distance is minimized, I'm going to find couplings that are regularized. So couplings such that the density, some L2 norm of the density of this coupling is penalized. And so I'm going to try to find smooth couplings. And when you add such regularity constraints to the coupling constraints in the earth mover distance, that translates to constraints in the Wasserstein formulation that are saying that correspond to smoother versions of the one Lipschitz constraint. So instead of requiring that the discriminator is a one Lipschitz function, that is replaced by a sort of a Lagrangian version of a Lipschitzness quantity in the loss function. And so now you, instead of having this hard constraint of Lipschitzness, you end up with a soft constraint on the smoothness of the discriminator function, and it's easier to optimize through gradient descent. And that also adds some extra strong concavity and strong convexity to the loss function that is employed in the Wasserstein GANs. Okay. All right. Some open problems. A wide open problem is that most of this analysis, most of the theoretical analysis actually looks at this idealized version where we're solving the population problem, and where at every step of the gradient we use all of the distribution or all of the data. There's not much work done to analyze the last iterate convergence or the limit behavior of stochastic versions of this gradient dynamics, where you sample data points at every period and you only have an unbiased estimate of the gradient. There's some existing partial positive results, but also some existing negative. A lot of the positive results really require a very strong assumption of strong convexity and strong concavity of the loss function. And there's some partial negative results that say without strong convexity, maybe there's no hope for methods that we know work without the noise. For example, this paper by Juditsky, I believe, showed that the extra gradient method might not converge in terms of the last iterate when you have a stochastic version of it. And next, okay, another open question is, an open-ended area is, can we say anything about finding local equilibrium solutions to non-convex concave games? Or instead of actually translating this to a zero-sum game, is there other ways to finding local minima of this min-max, of these max laws, right? So go back to the min-max laws and find critical, local optimal solutions with respect to the generator. So not try to formulate it as a zero-sum game. So the next is this bad or inexistent pure equilibria. Again, the problem is that because it's a non-convex concave problem, a pure equilibrium is not guaranteed to exist. There might be a large duality gap, and also local equilibria can be far from minimax solutions. And one line of work has tried to address this by, instead of optimizing over a single neural net, optimizing over mixed strategies, whatever that would mean. So some sort of expand the space of optimization. For instance, this work of Aurora et al. Says we should optimize over an ensemble of multiple neural nets, and then we can actually use multiplicative weight updates to weight these different generators and weight these different discriminators. And so we have gradient descent updating the parameters, simultaneously updating the parameters of all of these discriminator and generator instances, and then we have a global multiplicative weights against multiplicative weights player that tries to find mixtures of these two distributions of players, and that should sort of simulate finding an equilibrium in mixed strategies. And they actually do invoke results from results like the Lipton-Markakis meta paper, where they were saying we know by results in game theory that the equilibria will have small support, so we don't need to use mixed strategies over a huge support. It suffices to use a small support equilibrium, and that's how they motivated using a small set of generators and discriminators. Other approach like the one that Ashwin hinted at by Granarova et al., where they say instead of doing gradient descent, let's do follow the regularized leader. So we need to best respond to the past distribution of play of every player plus a regularizer. We cannot really store all of those generators and discriminators, so let's just store a window of it, and we're gonna, drop one by one as we go along. And then in the end, instead of returning the final neural net, we're gonna return a random draw from the distribution of neural nets of the generator in the final window, and that could help with this mode collapse by drawing from a mixture over generators. And also there's been some work by Rahul Savani where they consider another idealization of this GAN game where they only look at versions of the GAN zero-sum game, but where the strategies of both players are actually finite, and they look at the again, learning in mixed strategies over these finite zero-sum games. And they take this algorithm from finding NAS equilibria called the parallel NAS memory and translate it into how this algorithm would look like if you wanted to train a neural net. And they also saw some experimental results that it might avoid the mode collapse problem. So there are some ideas, again, by people in our community that might help. Another type of idea, which is similar in spirit, but the papers don't really phrase it exactly the same way, is to instead of changing the strategy space to be a mixed strategies, let's just change the whole game structure. Let's add multiple players, so we could potentially have many discriminators, or we could potentially have many generators. In fact, this many generators approach is very, very similar to the Aurora et al. Paper, as was also shown by this, argued by these authors. But in some sense, what the difference is that here you're not even learning over a mixture over these generators. You just have one player who is the discriminator and multiple players who are the generators, and they just play this zero-sum network game, this network zero-sum game, where this player's strategy affects all of its games with all of the generators. And similarly, this other paper does the same, but with many discriminators. Both of them are sort of trying to attack the problem of this minimax duality gap. Maybe when you go to more players, then there actually exists a pure NAS an equilibrium in pure strategies. And in fact, this paper here actually has some formal results on how the minimax duality gap shrinks as you increase the number of generators. Again, the open problems here, there are partial results, but I still view these as open problems to understand the space of local equilibria of the GAN game, of different GAN games, and how suboptimal this equilibria can be. We might be able to apply implicit approaches for characterizing properties of this equilibria. This is a recipe that has been proven useful in our community, like the price of anarchy analysis. Maybe we can apply such similar implicit approaches to argue about the quality of local equilibria of this GAN game, of this distribution learning game. And maybe we can design new distribution learning games that have provably only good equilibria, maybe multiplayer games, maybe non-zero-sum games. And maybe we can use ideas from solving multiplayer non-zero-sum games from our community to design algorithms for training for learning distributions in this complex structured data space. And so with that, let me just conclude. So the punchline is that GANs are a leading approach in research and practice to learn distributions over complex data like images. There are two main problems in training of generative adversarial networks that maybe our community can provide new viewpoints, such as computation complexity of equilibria, no-regret learning in games and polymatrix games, analysis of equilibria in games, and design of games with good equilibria. And there's been already several contributions from the EC and theory community in each of these directions, and many of them have actually received considerable attention from practitioners and people in the machine learning community. So there is a great opportunity to have immediate impact in machine learning practice. Thank you. Questions?
So you mentioned some work that's trying to quantify the gain at an equilibrium, but what guarantees that you end up finding one of those equilibriums that exist?
Yeah, so those games are mostly trying to mostly make the actual loss of the game to be strongly convex or strongly concave. And then there are some results from the theory community, at least without noise, that when you do gradient dynamics, assuming convex concave, when you do gradient dynamics, then they actually converge in terms of the last iterate. Now, the only hand-waving part there is what happens with the first few layers of the neural net. If you just look at the game that is played by the final layers, which is a convex concave game, then everything is fine. But now you're also changing the first few layers of the neural net, and that introduces some non-concavity and non-convexity, and maybe that will throw you away. But the hope is that those are stable enough that most of the game is happening from the final layer, and then you can reach an equilibrium.
Are there any approaches which try to combine the discriminator and the generator updates so that instead of updating them one at a time, use sort of joint update?
Yeah, I would say that so for example, like the extra gradient does do some coordination. Also, this Hamiltonian gradient descent that Jake proposed actually is a centralized. Now it's a centralized dynamic because you're trying to minimize the norm of the gradient of both players. So all of a sudden, it's an optimization problem, and it's not a dynamics problem. Those are the two things that come to mind. Yeah. Cool. Thank you, everyone, for coming, and yeah, thanks.